this chapter, we will be introducing the concept of integration. In this lesson, we will be introducing the definite integral.
All right, hi everybody. So now we're going to take a look at the area under a curve as a limit. And this is going to take us to something we call definite integrals. And I'm really excited to be getting to this point in the course here. Calculus is broken up into two different branches. There's differential calculus. That's what we've spent the majority of this course working on. Okay, the main idea there is the derivative, with the goal being to find the tangent to the equation of the tangent to the curve, the slope of the tangent line to the curve at any given point. That's the idea. In integral calculus, the main concept is, well, obviously the integral. And its purpose here, or its kind of driving idea, is to find the area under a curve. Now, we've already been doing that. We've been using antiderivatives to accomplish that goal. Now what we're going to do is we're actually going to create some notation that we're going to use. It's going to actually make all of this a lot easier. This finding the area under the curve a whole lot easier. Okay, so let's take a quick look here. We are going to introduce to you the definite integral. Okay. Now to start off with, we're going to let f be a continuous function. Whoops. Okay, we're going to let f be a continuous function on the interval a to b. Okay, I'm going to have a little bit more to say about that in just a second, but let's draw out this function here. So let's say here are our axes. Draw that down a little bit further here. So I've got this curve and it's doing something like this, and let's say that here's A and out here here's B. And so we're interested in finding the area under the curve. That's what our antiderivative is. We've been using that to do. We're going to create this thing called an integral that does this, and let me show you what it does. What I'm about to do here is really skip over a lot of really good math, and I apologize for that, but the point here is going to get a little lost if we go into a lot of detail. All I want to do is I want to show you in a very general sense what an integral looks like and what it represents. Okay, so the way we would find the area under a curve like this typically is we would break this thing up into rectangles. Okay, we're going to break it up into really the basic building block of determining any area, which is just a rectangular shape. So I'm going to create this little rectangle here, comes down, and then I'm going to move over a little bit, create a rectangle, comes down, go up to the curve, create a rectangle that comes down, rectangle that comes down, and as soon as my curve starts to bend down, you're going to see me go out beyond it a little bit, out beyond it a little bit, out beyond it a little bit, and so on and so forth until we get over to B. Okay? So now the idea being is we're creating all of these little rectangles, and they're all going to be the same width. Okay? And what might the width be of each one of these rectangles here? Well, I don't know. I know that the difference between A and B here is being chopped up into a certain number of pieces. Now, I mean, right here I drew a certain number of rectangles, but let's say we don't know how many I drew. Maybe I drew n rectangles. Like, again, clearly there's a specific number that I drew here. I haven't even counted them here. But let's just say that you drew n rectangles. Well, the width of each one here is going to be this little delta x. We're moving along the x-axis here. It's going to be a little change in the x-coordinate. Well, delta x, we can be a little bit more specific than that. The width of each one of these rectangles is going to be the value of b minus the value of a. And we're going to divide that by the number of rectangles we've got. And that's going to give me the width of each one of those. And that will be the width of every one of those rectangles. Now, the height of each rectangle is going to be determined by the function. Okay, so I go from A, I went up, came to the function, went straight over my delta x. So what I'm going to do to figure out what the area of that rectangle is I'm going to evaluate it at at A, so it'll be f of A. Okay, right there, that is going to be f of A. I'm going to multiply that by my delta x, by b minus a over n, and that will give me the area of that rectangle. For me to get to the next rectangle, the second rectangle, what I'm going to do is I'm going to use this x-coordinate right there. Okay, now that x-coordinate right there, we'll go over here. So my first rectangle was where x was equal to a. My second rectangle is going to be where x is going to equal a plus, well, it's going to be plus a delta x. Plus 1 delta x. Okay? Now, my next rectangle is going to be over here. I'm going to use that height to figure out the area of this rectangle. To get my next one, okay, this right here, this was going to give me the height of my second rectangle. So again, my first rectangle, its area, the first rectangle, maybe I should write it out like this because it'll make a little bit more sense here. The first rectangle, its area is going to, we'll say area 1 here, is going to be f of a multiplied by delta x. My second rectangle, well, that's going to be f of, well, a plus delta x multiplied by delta x. My third rectangle, and this is where I need you to really pay attention to what I'm doing here. My third rectangle is going to be f of a plus, well, to get to my third rectangle, I need to get to this point right here. That's going to be a plus 2 delta x's, and then multiplied by delta x. And if I want to get the fourth rectangle, that's going to be f of a plus 3 delta x's multiplied by delta x. So now if I want the nth rectangle, okay, the nth rectangle, that is going to be f of a plus, okay, n minus 1, or actually maybe I should say I'm going to say the ith rectangle. That might make a little bit more sense here, because I'm using n for the number of rectangles. I don't want you confused with that. So let's say I. Okay, so this is going to be to the I minus 1 times delta x multiplied by delta x. So that's going to give me the height of every rectangle here, one at a time as I go along here, multiplied by delta x its width. If I add those all up, okay, that will be the area under the curve. So here's what I'm doing here. I am going to get the area, to get my approximation with n rectangles, what I'm going to do is I'm going to start with I, and I is going to go to 0. Okay? It's going to go to 0. And because I'm starting at 0, and you'll see why I'm starting at 0 in just a second, but I'm starting at 0, and then I'm going to go up to n minus 1. Now, if I had started I at 1 and gone up to n, that would be n rectangles. I'm just adjusting these limits just a little bit. I'm going to start my sum at 0 and go up to n minus 1, and I'll show you why. You'll see it in just a second here. That way, for the height of each rectangle, I'm going to start at a plus I delta x. Okay, instead of incorporating a little minus 1 there, whoops, and I should have put that as the ith rectangle. Instead of having to do this I minus 1 here, which is what I had up here, I'm going to adjust that just a little bit. I'm going to let my I now start at 0, okay, and work my way up. And this will be multiplied by delta x. So I'm just avoiding needing to write this as I minus 1 in there. I'm just going to write I. So the height of each rectangle will be, is going to be determined by a plus I delta x. Now in this case here, though, I is going to be essentially 1 less than the rectangle that we're looking at. That's how you would do it. Now, this is going to be a rough approximation of the area. Okay? Because if you take a quick look at this, my diagram here, notice that on this side of the curve, as my curve is going up, my rectangles are slightly underneath the curve. Over here, okay, as the curve drops back down, my rectangles reach out to the side. I have this little bit of extra area going along here. So Here I'm a little less, here I'm a little bit more. It would be great if they perfectly balanced each other out, but I doubt that's going to happen. So I don't get a perfect area calculation by adding up all those rectangles. How do I make this better? How do I make this the area under the curve that I'm looking for? Well, what I do is I let the number of rectangles go to infinity. So I'm going to take the limit as n goes to infinity of I equal to 0 to the n minus 1 of f of a plus I delta x. Okay? So I'm just letting the number of my rectangles become infinite. And what that does when we do that, I'll flip this over and I'll rewrite this. Okay, so just to show you what we did here. Again, the area under my curve, and I'm going to say now the area under the curve from A to B is going to equal the limit as n goes to infinity of the sum as I goes from 0 to n minus 1 of f of a plus I delta x. This is the height of every rectangle. This is the width of every rectangle. Okay, remember that delta x was equal to b minus a over n. So that delta x is also being affected by this limit. This is the height as we go from one rectangle to the next, and we're going to add them all up. And we're going to allow the I to just be one less than the rectangle number that we're looking at. Okay, we add them all up, take the limit, so I'm going to get this infinite number of rectangles that are infinitely narrow here. This will give me an exact value, okay, for the area under the curve. Now, I understand that to be true. This is going to be equal to these two symbols together. Okay? These two symbols together right here are going to be written like this. What this is an elongated S, quite honestly. S for sum. This symbol right here refers to an infinite sum. Now, instead of writing f of a plus I delta x, because we're letting the number of rectangles become infinite, well, what happens here is that every single point along the curve is going to be the height for some rectangle. So I don't need to do that anymore. I'm basically just going to use the curve as the height. Now, I'm going to let n go to infinity, which means delta x is going to become this infinitely small little piece here. So instead of delta x, okay, so now we're going to look at this piece right here. Instead of delta x, I'm going to use a differential dx, and we'll recognize that from the notation that we introduced at the beginning of the differential calculus we looked at. Now, in this right here, I still don't have a sense along the curve of where I'm finding the area here. Up in my original question right here, I started at A, and because of the way my delta x was defined, there was a b implicit in there. That's not clear in this notation, so what we do is we put an a down here and a b up here to indicate what we the limits of our integration. We're going to integrate, or we're going to add up all the rectangles from A out to B. And this is what we mean by a definite integral, okay? This is the formula, or the notation that we use to indicate that we're finding the area under the curve of f of x from A to B. This is the height of each one of my infinitely small rectangles. This is the width of each one of those. And those are my limits of integration here. That's what this is. That's what that represents. That is the definite integral. Okay? This is a big step. Getting that notation down, that's huge. Now, a couple of things to note before we take a look at some examples here. First of all, when f of x is greater than or equal to 0 for all x in the interval from A to B, okay, whoops, a little low here. So if the function is positive for all x in that interval, then the integral from a to b of f of x dx represents the area under f of x from a to b. Now, bear in mind that you already know how to use antiderivatives to find that area. So what we're going to notice here is that this definite integral is implying that I take the antiderivative of that f of x. Okay? So that the derivative of my area function is equal to that f of x. And when I see this notation, it means find the area under that curve. That is, it is telling me to do the antiderivative. Now, another thing to be careful of, though, and we had looked at this before, but we're just going to state it again because it's going to become an issue again. Whoops, sorry, I keep bumping that. If f of x has positive and negative values, okay, positive and negative values in the interval a to b, then the integral from a to b of f of x dx, okay, is the difference in these areas. Now, oh, you can't see that, I'm sorry. So what I mean by that is, let's just say you've got a curve that does something like this, okay? Let's say it goes up, down, up, sort of thing here. And I'm finding the area from A out to, let's say, B. What this is going to do, okay, is this is going to create rectangles like this, here, here, here. And that's not a problem here. But once you get to this point right here, the height of the rectangle becomes negative. And so as a result, now the width is still positive, but the height becomes negative because it's going down. So this little area right here is going to be negative. Whereas this stuff up here, all of these rectangles here are going to have positive area. So when you add those all up, the result you're going to get is going to be these two areas minus this area. So the result is the difference between the areas represented by this function, between the function and the x-axis. Okay, so just to be clear here, so what we get here is the integral from a to b of f of x dx in this situation, okay, is the difference of the areas formed between the curve and the x-axis, okay, between the curve and the x-axis, above and below the x-axis. Okay, so the areas up top here, add those together, we're going to subtract this area below. So you gotta know that. Okay, you gotta know that before you go too far with this, because you got to be totally clear on what it is that this function is doing, this notation is doing. Now we can do an awful lot with this notation. Sometimes this is exactly what you want. You want the difference between those two. Let's just say, for example, that we're summing up values here. We're trying to figure out our company's total profits here. Well, if we go through a section where we had negative profits, I want that reflected. I want that information. That's important. Okay? If there are times when my function has negative values and positive values, and I'm adding those all up, but those negative values are significant, I want to include that. On the other hand, if I am looking for the actual area between the curve and the x-axis, well, then I don't want these negative portions canceling out positive values. I want to consider them separately. So what I would end up doing is breaking these up into pieces and adding those together. Now, before we take a look at some examples here, let's just get our vocabulary in order here. So here we go from a to b f of x dx. Okay, so that right there, this is the integral sign. Okay, it's just a big S, just a big stretched out S. And it just represents an infinite summation. Okay, infinite summation. Oops. Then we've got that we've got a and b. These are the limits of integration. Basically, we're finding the area from the low end here up to the high end, which basically means left and right. F of x is the integrand. Okay, it's the height of each one of those rectangles. So it's the function that we're looking for the area under. And d of x is the differential. And in this context here, you think of it as the width of each one of those rectangles that we're putting all together. All right, that's some really powerful notation there, really, really useful. In this particular course that I'm teaching, we are not going to have the opportunity to explore this in an awful lot of detail. I'll show you some applications here, and hopefully I'll get a time to make some more videos to show you some of the various methods of integrating. But for the course that I'm teaching this specifically for, we don't actually go all that far with this. Anyway, having said that, let's take a look at some examples. Okay, so this particular question tells us to evaluate the integral from 0 to 5, 3x minus x squared dx. Now, to get your head wrapped around what is going on here, what you got to remember is that what I'm setting up here is an infinite sum of all of the little rectangles that have a height 3x minus x squared and a width of dx from 0 to 5. So I'm finding the area under the curve. Well, now wait a minute. I know how to find the area under the curve. I remember that the derivative of my area function is going to, the derivative, of the area function is going to be equal to the function I'm finding the area under. It's always a confusing sentence here, but we've gone through that in the past here, so I'll just say it again. The derivative of the area function is equal to the equation or the function that I'm finding the area under. So what I want to do to get my area is I actually want to take the antiderivative of this. So that's not a big deal. I'm going to do that term by term. So this is going to become 3x squared over 2 minus x cubed over 3 plus c. And I remember that c is that constant of integration, okay, that arbitrary constant. And what it means in this context is that's what allows me to find that endpoint. Okay, when I create that area, I'm going to create it with respect to a left-hand endpoint. But I noticed before, okay, when I was doing my work here, I noticed before that I don't really need to specifically find that C when I'm looking for the area, especially when I know the limits of that, what we call limits of integration. When I know that I'm going to find the area between two values here, what I'll do is I'll just take my area function, evaluate it at these two endpoints, and subtract. Now, the notation that we use looks like this. So I found the antiderivative, essentially. Now what I'm going to do is I'm going to evaluate that between those two endpoints. So this is going to be 5 squared over 2 minus 5 cubed over 3 plus c minus 3 times 0 squared over 2 minus 0 cubed over 3 plus c. So just like I did in the past here, where I evaluated my area function at the right-hand limit and then subtracted the area function evaluated the left-hand limit, okay, now I'm just going to do that. I'm going to assume that my notation here tells me to do that. So this is find the area under the curve, okay, or the difference between the two areas, if that's what's going on here. And I know that I can do that by just taking the antiderivative of that function. I get that arbitrary constant, but I'm going to evaluate it between my two limits. Notice that c is going to cancel. And in fact, not only did the c's cancel, all of this kind of cancels, and I'm just left with 3 times 5 squared over 2. So that's going to be 75 over 2 minus 125 over 3. Okay, and I believe when you work that down, you're going to get negative 25 over 6. Okay, that's an interesting result. What does that mean? Well, what I know is that it's the sum of the areas of all of the rectangles that I formed under this curve between 0 and 5. But when I say under the curve, remember that could mean below the curve or above the curve. Under always sort of means to the x-axis. So to really get a sense of what's going on here, I sort of need to draw this out, okay? And it turns out that this function is going to look something like this. It's going to come up, and then it's going to drop down out here at 5, okay? And it's going to have an x-intercept here, and you can probably figure that out right away here, at 3. So here's what ends up happening. I end up with, whoops, this part of the function above the curve, and then I end up with this part of the function below the curve. So this bit right here is going to have a positive area. This is going to have a negative area. And when I add them up, my result is negative 25 over 6, meaning that there's more down here than there was up there. So this is the final result of adding up all of those areas. Now, that is the value of that integral. Done. I don't have to do any more. That's it. That's what I was looking for. But just so that you understand how I might adapt this here, what if the question was, let's change it down here, find the area between y equals 3x minus x squared and the x-axis from 0 to 5. Whoops, 0 to 5. Well, now that's a slightly different problem. And so what I'm going to do here is I need to understand what my function looks like. And I know that I'm going to have this positive portion here, I'm going to have this negative portion here. So what I'm going to do is I'm going to break this thing up, and I'm going to just throw the absolute value on here. And I'm going to find the area of the sum of the areas of all the rectangles from 0 to 3 of 3x minus x squared dx. Now, that's going to be this area right here. Didn't really need the absolute value there because it's going to be positive anyway, but that just kind of covers my butt. I'm going to kind of do that regardless. And then I'm going to add to that the absolute value of the area of all the rectangles. Whoops, sorry, don't know why I wanted to put 0 there. Not what I meant. I meant 3 to 5 of 3x minus x squared dx. So what I'm doing is I'm separating out these two areas. I'm going to find the areas separately, take the absolute value that's going to shear the negative off of this, and then I'll add those up. Now, it turns out the antiderivative is exactly the same. That's going to be 3 over 2 x squared minus x cubed over 3 plus c. I'll evaluate that between 0 and 3 and then take the absolute value of it. Plus, again, the absolute value, this is going to be 3x squared over 2 minus x cubed over 3 plus c. Whoops, I'm going to take that between 3 and 5 and take the absolute value of that result. Okay? So now this is going to be the absolute value of 3 times 3 squared over 2 minus 3 cubed over 3 plus c minus 3 times 0 squared over 2 minus 0 cubed over 3 plus c. Now, notice that this subtraction happens within these absolute values. So that c is going to disappear. Okay, it's going to end up having opposite signs here. I'm going to add to that, and I'll just offset this a little bit. the absolute value of this will be 3 times 5 squared over 2 minus 5 cubed over 3 plus c minus 3 times 3 squared over 2 plus 3 cubed, whoops, that's right, not plus, minus 3 cubed over 3 plus c. And that's all within the absolute values. Okay, so now when I do that, and I'm just going to kind of jump you to the answer here, okay, this is going to end up being the absolute value of 27 over 6, and this is going to end up being the absolute value of negative 52 over 6. Putting that all together, I'm going to get an answer of 79/6 units squared, whatever those are, as the area under that curve. Okay, so I hope that process there makes sense, and that the difference between these two questions is quite clear. When I ask you to evaluate this, I'm just asking you to sum up all of the areas of the rectangles under that curve, bearing in mind that some will have positive area, some will have negative area. That's okay. Add them all up. Slightly different problem. Now I want you to treat those separately. Get rid of the negative. Don't worry about it until the end. Don't worry about that negative until you get right to this end here. When we're about to combine these together, let the absolute value get rid of that, and then we add those together. Okay, let's take a look at another example. All right, let's take a look at another one here. So in this case right here, notice that all I've got is this expression. It's the integral from -1 to 2 of x cubed dx. Okay, now remember what this is asking me to do. I just want to evaluate the area of all the rectangles underneath x cubed from -1 to 2. Now, just one thing before we get into this, I want to point out that, look, this dx here, you need to write that there. That needs to be there. Please don't get in the habit of just doing that, writing that down. That dx identifies that x is the independent variable in this expression, so that when I take the antiderivative, this is the variable. Now, right now in this context, you might look at this and go, well, duh, yeah, of course it's the variable. That's the only variable there. But it's not going to take you very long in your calculus education where it won't be the only variable there. There will be an x and a y and a z, and the dx is going to help you identify at this moment, this is the variable. Then there might be a dy in there, and at that moment, the y will be the variable. Please, please don't stop writing that. You need to continue to include that here. Okay, now, remember how this works. The derivative of my area function is the function that I'm looking under. So to get the area, I need to find the antiderivative of that. And that's going to be x to the 4th over 4 plus my arbitrary constant evaluated between -1 and 2. Okay, and so now what I do is I'm going to evaluate that at my left-hand endpoint. So 2 to the 4 over 4 plus c minus, what do we got here? -1 to the 4 over 4 plus c. Okay, and we get 15/4 when all is said and done. Now, I don't exactly know what that is. I don't know if that's the area under this curve exactly, or if it's the difference between the areas under the curve. I don't know unless I graph it. Okay, all I know is that that is the value of the sum of all of the little rectangles from -1 to 2. If I want to know what it is, I have to look at the graph here. Now, turns out that's a pretty easy one to get my head wrapped around. Okay, because a cubic function looks like this. Yeah, something like that. Now, from -1 to 2, -1 to 2, this bit right here is going to have a positive area because it's above the curve. This is going to have a negative area because it's below the curve. So that result that I found just there, that is the difference between those two areas. That is, though, the answer to this curve. But I could change this. I could have a different question. It could have been find the area, okay, under y equals x cubed from x equals -1 to x equals 2. And that is a slightly different problem. My area is now going to be the absolute value, okay, of the integral from -1 to 0. Okay, because I can see that's my x-intercept here. That's the kind of the boundary between them. That's going to be x cubed dx plus, again, the absolute value of the integral from 0 to 2 of x cubed dx. Okay? And so now this is the absolute value. This will be x to the 4th over 4 plus c between -1 and 0. And this will be the absolute value of x to the 4th over 4 plus c from 0 to 2. Again, in the absolute value here. So absolute value, this is going to be 0 to the 4th over 4 plus c minus -1 to the 4th over 4 plus c. Again, in the absolute value. This will be 2 to the 4 over 4 plus c minus 0 to the 4 over 4 plus c, all in the absolute value. Okay, now I have already done this, set this up. So this is going to end up being the absolute value of -1/4, and this over here actually becomes 4. And when you put that all together, you get 17 over 4 units squared. That is the value for the area, the total area under that curve. So notice the amount of work required. When you want to figure out the area under the curve, you got to split that up, break it into its pieces here. Okay? Whereas evaluating the integral doesn't require that. You just take the antiderivative and then evaluate that between the two endpoints and then find the difference. That's all you got to do. So I'm going to stop right here, and we're going to come around and in the next video here, we're going to look at some applications of this, ways of making this easier to do.